So let's take our arrays to the next level, or I should say the next dimension. We're going to talk about multi-dimensional arrays. So everything that we learn to do with one-dimensional array can be relatively easily generalized to n dimension, n being arbitrarily large. Okay, so we can have two-dimensional arrays, matrices. Okay, we can have a three-dimensional array, four-dimensional arrays, and so on and so forth, as large as you need. So let's jump into code to see how we can manipulate those multidimensional arrays. So first, the definition. So I'm still going to use arrays of elements that are int. But as I've been saying in the previous videos, everything that I teach you to do as an array with an array of int can be done with an array of double, an array of float, an array of long. You can change the data type of the element very easily. Everything else remains the same, remains true, right? Everything else that we covered and studied together. So here, instead of having an array of one dimension like this, for example, an array of 5 int, I want to have an array of a matrix of 2 rows by 3 columns. And the convention is that the first dimension generally is seen as the number of rows in your matrix. The second dimension is the number of columns. And then as we go higher and higher in the dimension, the analogy breaks down a little bit. We are just calling them third dimension, fourth dimension, fifth dimension, etc. But the idea is when you define an array that is multidimensional, you use the same recipe that we use for one dimension, but you use that square bracket notation here that you were relying on to specify the dimension of your one-dimensional array. You use it again after to specify the size of the second dimension. And if you want to keep going like that, you can definitely keep going like this. Okay, so you can have as many dimensions as you want, and then you end this with a semicolon. Okay. All right, so we have here, for example, a three-dimensional array that has 2 rows, 3 columns, and in each of those elements, there's going to be 5 int values. Okay. All right, so let's take something that's a little easier to visualize. Okay, 2-dimensional is easier to visualize. 3-dimensional, stretching it a little bit. 4, 5, 6, 10. 123 dimension, very hard to visualize. So we're going to stick to, for most example, to 2 dimension. Here we have a matrix that is a 2 by 3 matrix, 2 rows of 3 columns. So each row contains 3 elements. So how can we, before we move any further, how can we define the sizes here of our multidimensional array? So we can obviously use literal values like 2 and 3. Okay, these are known at compilation time, not a problem. The same way that we were able to use pre-compiler symbolic constant with our one-dimensional array to define the size, well, we can use those again, to define, for example, NB rows is going to be 2, and then define NB columns is going to be 3. And once I have those symbolic constant defined, I can use them here instead of 2 and 3, NB rows, NB calls, okay, NB columns. So let's compile to make sure that, I show you that what I say is actually acceptable and accepted by the compiler, okay? So I can declare the sizes of each dimension with literals. I can declare them with pre-compiler symbolic constant. I can declare them using also constants. So here we are, let's declare 2 constants, const int, and I'm going to call it NB rows equal to const int. I'm going over all the possibility of the option that are available to us, okay? And if I have those constants, well, then I can use them here. And the ID is the same, okay? The constant is known at compilation time. The pre-compiler macro define a symbolic constant at pre-compilation time. So by compilation time, it is also known. So all of those are relying pretty much on the same ID, okay? When I define my array, I want to know its size at compilation time. And all those versions are working just fine. Now, since the introduction of variable length arrays, we can have variable length arrays in one dimension, which size is defined at runtime by the content of a variable or by an expression that can only be computed at runtime. Well, the same is true also for multi-dimensional arrays. So if I remove those const keywords, these are no longer constants. I could have just read them from the user, for example, and I can still define my multi-dimensional array like this. So it's going to be technically a multi-dimensional variable length array. Okay. All right. So these are like not some. I think these are all of the options that are available. Okay. Literal, symbolic constant, constant, and then variables, or more generally expressions that are evaluated at runtime. And this is it for the definition of the array itself. Now, if I want to initialize that array with values, for example, well, I'm going to have to use a loop. For one-dimensional array, I need only one loop, where the loop goes over every element of the array. For multi-dimensional array, generally I need multiple loops. There are ways to write things differently so that I don't use multiple loops, but the most intuitive way to iterate over every element of a matrix, for example, a 2x3 matrix, is to say for each row in the matrix, and then inside that loop, for each element in the row of the matrix, so for each column in the matrix, do something. Okay? So that gives you this kind of like two nested loops for 2 dimension. If I had a third dimension, I would use 3 nested loops, 4 dimension, 4 nested loops, and so on and so forth. So let's take a look. So I'm going to use a for loop for size t. So I'm going to call it row so that it actually makes sense better than I or j or something like that, right? Row is lesser than nb rows, row plus plus. And then inside that for loop, another for loop for size t, column equals 0, column lesser than nb calls column plus plus. Okay. And for example, I'm going to say that data index, my first index row, and index, my second index column for the second dimension is equal to, well, I don't know, maybe like, maybe something like a number for all of them, 42. And then we are going to display this, and to display again, I'm going to take this, and I'm going to, this time, printf %d. Okay, and I'm going to actually display more than just the value, so I would display the value like so, the value of every element, but I want to do a little bit more than that. I want to display something like data index, so the first index, and then the second index, and then the value. Okay, so that looks a little bit more readable on the screen. So I'm going to display the first index is row, then column, then data index row and column. Let's save this. Let's get rid of compilation error, if any. There we go, none of them. Let's run this. So I forgot to put a backslash, and I'm going to add this because this is really unreadable. Okay. I initialize all my elements with 42, and what we're going to see here in a second is that indeed all the elements inside my array have been initialized to the value 42. So the rule is you have n dimension, you are going to have n nested loops if you want to iterate over every element of the array, whether you want to display those values, whether you want to initialize them to a specific value or do other things that we're going to learn to do in a few seconds, right? That's the generic rule about the design of your code. Okay, n dimension, n nested loops. Okay. There are easier way to initialize an array. Okay, this is maybe the most flexible, the most generic, but if I don't want to use, for example, a loop here or a series of nested loops to initialize my array, maybe what I want to do is I want to use that syntax that we covered for one-dimensional array, using the curly braces, the initializer list. So for a one-dimensional array, I would just put my values separated by comma. Okay. But here, I don't have just one dimension, I have 2 dimensions. So that means that I have a certain number of rows, and inside those rows, it's like I have an array inside an array, right? Inside the rows, inside each row, I have pretty much a certain number of elements, one per column. Okay, so that's going to be exactly how we write this. We are going to say that if we have two rows, okay, I'm going to have two list initializer like this. So there we go. This is saying my matrix, okay, my 2 by 3 matrix is going to be initialized with some elements that go in the first row, some elements that go in the second row, so there are two rows. And how many columns I have? 3. So 1, 2, 3, 4, 5, 6. Okay, 3 elements per row. So that's going to give me indeed a 2 by 3 matrix. So most of the time we note this like so. We go to the next line. Oops, I didn't mean to leave the curly brace alone there. We go to the next line, and every time we go to the next line for a new row. Okay, that allows us to keep things very readable. And then this is the end of our matrix. Oops, here. Keep things really readable, and it actually allows us to look at this and see immediately this is a 2 by 3 matrix. Okay, first row contains 1, 2, 3, second row contains 4, 5, 6. And because I'm using the initializer like this, the size will be known at compilation time. I don't need to specify the size of any of my dimensions. They are going to be pretty much inferred by what I write here in the initializer. Let's take a look real quick. Save this, compile. So I forgot something, array type as incomplete element. Yes, I did forget something that we're going to cover also at the end of the video when we deal with parameters and functions. Well, with one-dimensional arrays, you can actually specify no size and let the initializer, for example, do something like that. Okay? All right, that's perfectly fine. That doesn't work, as you can tell by the compilation error, that doesn't work with multi-dimensional arrays. That's an important thing to know, okay? With multi-dimensional array, you cannot actually omit all the dimension. In fact, the only dimension that you can not specify in your definition of the array is the first one. So I could say I'm not going to specify the first dimension, but I have to specify the size of every other dimension. So we're going to learn exactly why this is so when we cover pointers, okay? But for now, please accept it as just as a rule, as an arbitrary rule maybe, but as a rule nonetheless. And we are going to say here that we have two rows of 3 columns, so we need to put a 3 here. Let's try to compile this, see if this is more acceptable by the compiler. Yes, it's more acceptable and it works. So of course you can go ahead if you want and you can specify all the dimension. Okay, we're going to discuss again a little bit more about why it can be useful to not have to specify all the dimension when we talk about pointers. Okay, but right now the rule is specify all the dimensions when you use an initializer list, or specify at least all the dimension but the first one. Okay. All right, so we have different ways of initializing. We have way of iterating. Once you understand how you iterate over an array, you can start doing interesting things. Like, for example, you can start saying, I'm going to look for the minimum value in the array. Okay, so I know these are int values. I'm going to further assume that my values in the arrays are going to be positive, just for the sake of this example. So I'm going to say that my min value in the array is equal to minus 999. Something that is so small that it's smaller than anything in the array, okay? And then I'm going to use the same template here that I had with those for loops. I'm going to say for size t. So again, row equals 0. Row, it helps to have names for the index that actually correspond to row and column, to make it easier to follow the logic of the code. And be rows, row plus plus. And then inside that for loop, again, for size t, call equals 0. Call lesser to nb call plus plus. So same logic, okay? 2 dimension, I want to consider every element, therefore I need 2 counter control loops. Okay, and now what I'm going to do is I'm going to test if the element at index row and call is actually lesser than the mean that I have currently, then I'm going to say my new mean is data index row and col. Okay? And then at the end, after I'm done doing all this, I can say mean is %d, and I'm going to display here the value of mean that I found. Let's see if that compiles, and then if that works. gcc main.c, a.out. So 1, 2, 3, 4, 5, 6, the minimum is minus 99. Yeah, no, that's not, I mean, technically true, right? If I start with a minimum of minus 99, 999, then yeah, that's the minimal value in the matrix for sure, because all the values are positive. So what I did here is I reverted the logic in my mind, and I said minus 999 because I was thinking I'm looking for the max. So if you're looking for the max, you initialize with the smallest possible value. If you're looking for the mean, you are initialized with the largest possible value that you're going to find in your matrix or in your array, right? So now that I use 999 and I can double check that it's indeed larger than any element in my array, right? I'm going to compile, I'm going to run it, and this time it tells me the minimum is 1. If I was looking for the maximum, then I would change this into a greater than, okay? I would probably change the name of the variable from mean to max everywhere, and then I would initialize it saying that my maximum is actually minus 999, and then it would make sense, okay? Because everything I find, like the first element I find in my matrix is going to be bigger than minus 999, so I'm going to replace the max quite immediately, okay, at the first iteration. And I'm going to run that again, and there we go. This time the max is 6. Okay, it's a little annoying to have to assign to mean or max respectively an arbitrary large and arbitrary low number, just that's not going to appear in the matrix and stuff like that. So we can do better than this. We can go here and we can refine a little the design of our code here and say, you know what, the max is going to be the first element of the matrix. Okay, and so that means I could theoretically skip it, not to consider it when I'm looking at all the elements, because I already said this is a max. But I'm going to keep it simple, so I'm going to say I'm still starting at row equals 0. I'm still starting at column equals 0. I'm going to compare this first element to all the elements in the matrix, including itself. And if I find one that is bigger, then I'm going to update what I know to be the maximum value in the matrix. Let's see if that's still working. A.out, the max is still 6. Okay, no problem there. So the logic for looking for the minimal value in an array and looking for the maximum value of an array, you can see how it applies also to n-dimensional arrays. The only technicality, the only problem is that you have to go from using one loop in a one-dimensional array to multiple loops in a multi-dimensional array. If I was interested in also getting here the max, the row of the max element, the coordinate of the row of the max element, okay, I would say it's 0 to start off with, then I would say max col equals 0. Okay, so this is going to be the row at which I found the maximum element in the matrix, the row at which I find the column at which I find the maximum element in the matrix. So because I decide to initialize my search by saying, you know what, let's pick the first element and we are going to assume it's the max, I set the row and column to 0 as well, which are the coordinate of this assumed max element. And then I go through every element of my matrix, and the difference is going to be that when I find something that's bigger than my current max, not only I'm going to update the value of max, but I'm going to also update the value of, so let's see, max row, and this is going to be the row that I'm looking at right now. Max col is going to be the column I'm looking at right now. And I can see here that it's been found at indexes, and I'm going to do %d, %d, and I'm going to put row and col here as my indexes that I'm displaying. So I should, could, will maybe use size t here for actually max row, max column. Okay, so I'm going to compile this real quick. So row undeclared, hold on a minute. Col and row are undeclared first using this function. Yes, it's because this is not row and col, this is max row, and this is max col. There we go. All right, let's try again. Main is out. So it's telling me that the max element is found actually at coordinate 1 and 2. So first row here, second column. So yeah, that's correct. But again, what I'm doing here is that I'm kind of like being lax with the data type of my indexes. So anytime you have something that represents an index in a matrix, in an array, etc., I told you should really be using the size t data type. So that's what we're going to do right now. We're going to do here %d becomes %zu, %zu, and it's not going to change much, right? There was an implicit conversion that was done by the compiler, so it was still working, but now the code is actually more proper, I would say. So following the standards a little better. Okay, expectation that other programmers are going to have on your code, well, now you're going to make your coworker happy instead of making them angry. All right. So we have a bunch of stuff here that we covered already. Okay, initialization with initializer, with all sort of possible size definition that we have, from literal to precompiler assembly constant to variable. We wrote a piece of code that iterates over all the elements of the array to display them, then to initialize them with a value originally. Then now we have been looking for the mean and the max. So if I wanted to make the sum of all the elements, you should be able to do that based on those examples. So do it as a quick exercise, okay? Pause this video, go ahead, try to do that piece of code that's going to compute the sum of all the elements of a 2x3 matrix, and then come back. And if you have problem, come to office hours. What we are going to do next in the video, we are going to jump to talking about how those multi-dimensional arrays are playing with functions. So we have a bunch of loops here. Everything is in the main. This is horrible. So let's do a little bit of spring cleaning. Void display matrix. And I'm going to get a matrix as a parameter. So this is going to be an int 2-dimension. Okay. Doing a little bit of Java notation there. Oops. And then I'm going to have an int that is going to be nb rows. An int that is going to be nb calls, and I'm going to make this a little bigger. There we go. Okay, nb rows, nb calls. And then inside, what I'm going to do is I'm going to, for example, display the content here. So display matrix. I want to display what is inside of data 2, 3. Okay. I can specify these as variables, as expression, as whatever I want. And I want the display code to be actually hosted inside this nice little happy function here. So let's see how many compilation errors we have here. Let me make this little. We're going to switch back and forth. We're going to play switch over there. So implicit declaration, yes, the prototype is missing. So let's go and do that. Here we are. Up. Prototype is going to be before the main. Semicolon. So I'm going to leave the name of the parameters. Sometimes I remove them when the names are like things like I, J, X, that do not really help. Here it really helps me know that I need to specify the number of rows first and the number of columns next. Okay, so I think that's useful to leave the name there. I'm going to save this file. I'm going to go back here, and we are going to recompile again. And now we have array. This is an interesting error. Array type as incomplete element type. Okay, so when I declare matrix empty square bracket, it doesn't like it. It tells me this is not a complete data type, pretty much. And we already encountered that. Okay, we encountered that when we were defining multidimensional array. The problem is that you cannot, unlike one-dimensional array, you cannot completely omit to specify all of the sizes for all the dimensions. As a matter of fact, the only size you can omit to specify is the first one. Okay, so let's fix that. In this case here, I could use like hard-coded values. I could use again precompiler pound define, macros to make symbolic constant that I use here as well. Or I could use a variable length array, features, and say that here pretty much this is going to be the same as NB rows, and this is going to be the same as NB calls, referring to the NB rows parameter and the NB calls parameter here. Let's try to see if we can get away with that. There we go, GCC main.c. So we are not getting away with that exactly here because it says NB rows is undeclared, NB calls is also undeclared, and so on and so forth. Okay, so we are going to change a little bit things here, just a little bit. Let's make our compiler happier by actually selecting this and putting it ahead of the expression of the declaration of the parameter int matrix NB rows NB call. If we're going to use the name NB rows NB calls, we need them to be defined here as parameter beforehand. So that's going to change my definition of the method, not by much, okay, but I need to go down here because I changed the prototype. I'm going to change also the definition here. There we are. So I just change the order of the parameters pretty much, okay? And then when I call finally the function here, there we go, I need to specify the size 2 and 3 before I pass actually my matrix. So all of this is saved. Let's see if I forgot something on the way. We're going to compile again. Data undeclared in display matrix. So line 42, let's see, that should not be a very interesting error. Let me make this a little larger. There we go. Did I use the wrong name? Yes, I did use the wrong name. Data is a variable in the main. Matrix is actually the name of the parameter. So I did the cut and paste of the for loop. I should have been careful about this here. GCC main.c. Now it's compiling a.out. So it's still providing the same feature. We just refactored. Okay, that's a technical term when you change the code of a program but don't add or remove any feature. You are refactoring it. I refactored my code. I'm now using a method that takes as parameter a multi-dimensional array. Again, I can specify all the dimensions, and I can do it with literals, with precompiler, symbolic constant with constants, or with, like in this case, parameters, so using the variable length array features that have been introduced in the C language. And then I can call that method, have it display. I could do the same thing with this piece of code here. Okay, finding the mean, I could go ahead. I'm going to do that real quick. Okay, so I could go ahead here and say, you know what, we're going to turn this into a function. So I'm going to return just the value of the mean, of the max. Max is %d, because I can return one value from a function, okay? And I'm going to call find max with my matrix of size 2, 3, and this is where the data is. All right. So find max, the size of the matrix, and then the matrix itself. Let's go down here, and I'm going to say, okay, so find max is going to return a value of one element, but all my elements are of data type int, so that value is going to be of data type int as well. Find max, here we are, int NB rows, int NB calls, int matrix, and this time I'm not going to forget to change the name as I paste the code from the main method. That will work a lot better. There we go. Paste the code from the main. Let's see, int max is going to be equal to matrix index 0, 0. We have max row, we have max call, and we have here matrix instead of data. Again, matrix instead of data. And at the end, I return max. And because I don't care about, the row and the column at which the max occurs, I can go back to the old version of my code, the initial version that I had of the nested for loop here, where I just look for the max, okay? And I don't care about specifying where it occurred in the matrix. There we go. So do we have to update? Yes, we have to update our prototype. So here's find max. We're going to not update the prototype, actually create the prototype. It's not even there to start up with. Here we are. So we have a prototype. We call it here. We define it at the bottom of our file. Let's save and see what else we need to take care of. Nothing from the compiler point of view. Let's run it. Are we still finding the max? Yes, we are still finding the max. There is just a little glitch here, you can call it that, a little typo here in the display. But other than that, yeah, it's still performing the same way that it was before, so we just refactored it. So we have been using those methods to illustrate how to define, how to declare parameters in a method that are multi-dimensional arrays. And I still have repeated this rule again and again, which is, you have to specify all the sizes of all the dimension, or you can omit only the size of the first dimension. So let's clarify a little bit what's going on with this, okay? Let's say that I have, why do we have to do this, pretty much? Let's say that I have a matrix named data, okay? And I'm going to take a specific size so that it's not too bad to do the computation by hand. I'm going to say it has 2 as its first dimension, 4 as the size of its second dimension, and then what did I take in my example? 3. 3 as its third dimension. Okay, and then let's say that here I'm going to fill this matrix with some data. So I have a 3-dimensional matrix. Now, in order to explain to you why that size of the first dimension does not matter, why we are capable to omit it anywhere, everywhere actually, but this one, the 4 and the 3 have to be specified constantly, okay? I need to tell you a little bit more about how this kind of stuff is stored in memory. You would assume that it's stored, in 3 dimension, like conceptually it's stored in 3 dimension, okay? This is a matrix that has elements inside of it, and it's a 3-dimensional construct, okay? So sure, that's how we visualize it in our mind, okay? But in memory, that's not how it's stored at all. The way it is stored, actually, is that we have said here that we have at the base 3 elements. So here's my 3 int, okay? We have 3 elements in that dimension. How many times do we find that dimension? 4 times. So here's a group of 3. Here's another group of 3. A third one. And a fourth one. And I'm storing all of this linearly, as if it was just one vector, right? So I have 4 here. If I start reading here and read like this, I have 4 rows of 3 elements. So here are my 3 elements. Here are the 4 rows of 3 elements. But wait, this is not all. I have actually 2 rows of all of this. 4 rows of 3 elements. So all of this is going to actually happen 2 times in a row in memory. So how many elements do I have total? And I erased here some stuff, so I'm going to add it real quick. Okay, so I had 2, 4, and 3 for the last dimension. So how many elements do I have total? 3 times 4, 12. times 2, 24. Okay, that's the total number of elements in my matrix. How many elements do I have here? 3, 6, 9, 12, and then this is again 12 elements, so 24. So yes, this is actually storing everything in the matrix, but instead of storing it in a 2-dimension or 3-dimension structure, it's simply storing it in memory like this, you know, one item after the other, like if it was a giant vector. Well, now the problem is if you call this element at index 0 and the last one is element at index 23, how do I convert something like, for example, data x? So x is going to be an index, right? Y, z equal 42. Whenever I try to access an element in that multidimensional matrix, how am I going to convert those x, y, z coordinate into a single number, a single index that is between 0 and 23? Well, I'm going to take the size of this. How many elements do I have here? I have 12 elements. And then I'm going to take my first index, x, multiply it by 12. Okay? Then I'm going to add y, multiply it by, so this time I need just this number of elements, 3, plus z. That is a formula that's going to allow me to convert x, y, z, set of index, like coordinate x, y, z in the 3-dimensional matrix, into a corresponding coordinate in that 1-dimensional storage of the 3-dimensional matrix. Okay, let's see how that works. So we're going to take an example. We're going to say, for example, we are trying to access data index. So the first index is going to be 1, then 0, then 2. So if I plug that in my formula, I'm trying to assign the value 42 to that element. Okay, if I plug that in my formula, I get 1 times 12 plus 0 times 3 plus z, which is, in this case, 2. This is a 0. Okay, I do this, so that gives me 0 here plus 2, so that gives me 14. Okay? All right, so that means what? That means that the element at coordinate 1, 0, 2, 1 for the first dimension, 0 for the second dimension, and 2 for the third dimension is located at index 14 in that 1-dimensional representation of the whole matrix. So 0, 1, 2, 3, 6, so there's going to be 0, 1, 2, sorry, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This is the element at index 14. This is where we want to assign 42. Does it correspond to the first row, 0th column? So the second row, sorry, start counting at 0. The second row, first column, and third element in that position? Yes, it does. This is here 1, 2, 3, 4, 1, 2, 3, 4. This is actually my first row. So this is the beginning of the second row. So row index 1. This is actually the column index 0. So we are still inside that column. And this is the element, the third element, index 2, inside that column. So yes, we have a conversion that works between the way that we conceptually visualize multidimensional array and conversion to the way that the C language actually stores multidimensional arrays in memory. Okay? And all of this to say what? All of this to say that when I look at this formula, okay, to be able to make that conversion, what do I need? I need 3. 3 is the size of the third dimension. Got it. So that means that anywhere I need to know the size of the third dimension to be able to do that conversion. Then I use 12. What is 12? Well, 12 is the product of the size of the second dimension multiplied by the size of the third dimension. So that means I need to know the third dimension size. I need to know the second dimension's size as well to compute that 12. Okay, 4 times 3. At any point here, do I use the 2? No. And the handwriting might actually confuse you because this is a z Okay, this is not a 2. This is a coordinate here. Sorry about that. But do I use actually the size here of the first dimension, the 2, anywhere in that formula? No, I don't. That's why I do not need to specify. You can specify it, you may specify it, that's your choice, but you do not have to, it's not required. Okay? So that's where that little constraint that we have been carrying all along during this video comes from. Okay, so I hope this makes sense. If it doesn't, you know what to do. You know where to reach us, so don't hesitate. Us, I mean myself, the TAs, etc., or even discuss this with classmates. Come to office hour and so on and so forth. Don't hesitate to ask any question, and I will be glad to address them. We're going to wrap it up for this video on multidimensional arrays. And again, as always, thank you for your attention.